If you have a no start or hard start condition, glow plugs could be at fault. However, before you get into glow plug system diagnosis, be sure the fuel system is okay. Be certain there are no air leaks in the system, that injection pump timing is correct, and that fuel is being delivered to the injection nozzles. Also, be certain the cranking system is capable of cranking the engine at least at 100 RPM when the engine is cold. On 6.2-liter engines, the glow plug system consists of a 6-volt glow plug at each cylinder, which operates on 12 volts, a glow plug relay, a glow plug controller, and a glow plug indicator lamp on the instrument panel. Other electrical components which have no function in controlling glow plug operation but are a part of the electrical system's start and run operations are the fuel solenoid, fast idle and cold advance solenoids, and the cold advance temperature switch. We'll limit our discussion here to the glow plug system on 6.2-liter engines. The glow plug heats the air in each pre-chamber 1400 to 1700 degrees Fahrenheit. Approximately 1700 degrees is needed for starting at 0 degrees ambient temperature. In 0-degree weather, the glow plug can heat the pre-chamber in about 8 seconds. The glow plugs are not designed to burn continuously, but cycle on and off as needed. The glow plug relay on the inner fender provides current to the glow plugs. The relay is pulsed on and off by the thermal controller. Before attempting any diagnosis of problems in the glow plug electrical system, be sure all electrical connections are installed properly and that they are clean and tight. Pay particular attention to the ground connection at the right rear stud on the air intake manifold. Loose connections have been found here on some 6.2 engines in 1982 models, which caused the glow plug system to malfunction. In carrying out any diagnostic procedure, do not bypass the glow plug relay with a jumper or attempt to manually operate the relay. Remember, the glow plugs are 6-volt heaters operated on 12 volts. If 12 volts are applied continuously for more than about 12 seconds, it'll burn out the plug. If burned out glow plugs are a part of the hard start or no start condition, the controller should be checked for proper function. This check should be performed rather than simply replacing the controller, since it's been found that burned out glow plugs or system malfunction is not always and in fact is seldom the fault of the controller. The controller is mounted in the water passage at the rear of the engine. Thermostatic elements within the controller cycling of the glow plug. The correct controller for the 6.2-liter engine is white with a silver label. Controllers with different color identification will not work satisfactorily in the 6.2-liter engine. To perform the controller functional check, first connect a VOM meter between the negative side, that's the blue wire of the power relay coil, and ground. Be sure not to short the positive terminal to any metal object. Turn the ignition switch on and monitor the meter. You should get 0 volts for approximately 4 to 10 seconds, depending on coolant temperature. If the engine is hot, you may get a continuous voltage reading of about 12 volts. The meter should then begin to show an on-off cycle of 0 to 12 volts. The power relay should also be heard clicking on and off. If it does, the controller is okay. Now, remove the positive lead of the meter to the power relay coil and connect it to the relay output. With the ignition switch still on, the meter should continue to repeat the on-off cycle. This indicates the proper voltage is being applied to the glow plug circuit. The controller has a 6-pin connector. As part of an electrical diagnosis procedure, you may want to check these connector circuits. With the meter at pin 1 of the connector, you should have continuity, 0 ohms resistance, to the brown wire at the alternator with the engine off. With the engine running, you should have alternator voltage at pin 1. If there is battery voltage at this pin with the key off, then diodes have failed in the alternator. There is no electrical connection at pin 2. Do not ground this pin for any reason. It will destroy the controller. On 1983 vehicles, there may be a white wire or white tube to this pin. It's not hooked to anything in the wiring harness. It's only there to seal the position in the connector. On 82s, this connector may be open. At pin 3, the blue wire, you should have battery voltage with the key on. At pin 4, an orange wire in most cases, but maybe green, you should have continuity to the double red wire terminal on the glow plug relay. Pin 5, the black wire, should have continuity to pin 6 and to ground, and the same for pin 6. Black wires from pins 5 and 6 are joined together in the harness and grounded at a stud on the intake manifold. Check for a tight connection here. Even an intermittent ground of pin 5 can burn out the glow plugs. Diagnosis charts to guide you in checking the controller heater circuits and other glow plug diagnosis information are in your maintenance manuals under the heading Engine Electrical. Another condition you may encounter on diesels is a loud knocking sound, something similar to a rod knock. It could be accompanied by excessive black smoke. This condition can be caused by a particle of dirt or metal chip in the fuel system becoming lodged between the nozzle needle and body, preventing the needle from seating. A nozzle that's stuck open can be located with a sounding bar. Another method is to open the nozzle fitting enough to allow a small amount of fuel to bleed off. If the nozzle is stuck open, cylinder compression will aerate the fuel, causing heavy foaming when the fitting is cracked open. An important point to remember here is that a stuck injector will often affect the cylinder that follows in the firing order. If injector number 5 were stuck, for example, it could cause injector number 4 to miss, 4 being the cylinder following 5 in the firing order. The reason for this is pressure in the rotor head is bled off by the stuck injector, so part of the following injection cycle is lost in making up the pressure drop. To remove a nozzle you suspect is malfunctioning, use the correct tool to avoid damaging it. To remove and replace Bosch nozzles on the 6.2-liter engine, it's important to use a 30-millimeter socket, tool number J29873. Don't attempt to remove them using the smaller hex on the upper part of the nozzle. This could break the seal between the upper and lower sections. And if you subsequently put the nozzle back into the engine, use a new sealing washer. It's also important to apply an anti-seize compound to the nozzle threads before reinstalling. Use GM part number 1052771 or equivalent. This will make removal far easier if you have to remove the nozzle again at a later time. Any nozzle you suspect of malfunctioning should be tested on a reliable nozzle testing device before you make any decision on replacing it. A nozzle tester can be used to check opening pressure, chatter, leakage, and spray pattern. However, because of the design characteristics of the Bosch nozzle used in the 6.2 engine, a pop tester cannot deliver enough velocity to obtain a meaningful spray pattern analysis. The checks that are most important in determining the condition of a used nozzle are opening pressure and leakage. In using a nozzle tester, refer to the manufacturer's instructions for exact test procedures. Be careful to keep your hands and arms away from the nozzle tip when testing. The high-pressure atomized fuel has enough power to penetrate your skin and cause injury. And keep a receptacle under the nozzle tip to contain the spray. With the nozzle connected to the tester, fill and flush the nozzle with test oil by pumping the lever several times. This forces oil through the nozzle and purges it of air. The first test is for opening pressure. Each test should be performed separately. Don't try to do two at once. Open the shutoff valve at the pressure gauge 1/4 turn. Then depress the lever slowly. Some nozzles will pop, others will drip fuel at this point. The important thing is to observe the maximum pressure at which the nozzle pops or begins to leak down. This is the opening pressure. For used Bosch nozzles from the 6.2 engine, the pressure should not be less than 1500 psi. For other nozzles, check the appropriate service manual for the correct opening pressure. Next is the leakage test. Keep in mind that each test is performed separately. Don't be concerned about opening pressure when testing for leakage and vice versa. Now, to perform the leakage test, open the shutoff valve at the gauge 1/2 to 1.5 turns. Blow the tip dry with compressed air. Depress the lever until the gauge reads 1400 psi. Look closely at the tip of the nozzle. There should be no obvious signs of leakage. A drop of fluid may form on the tip, but it should not fall off for at least 10 seconds. If it does, the nozzle must be repaired or replaced. When testing for chatter, keep in mind that the sound for new and used nozzles may vary. The carbon buildup in a used nozzle can produce a different sound than that of a new nozzle. To perform the chatter test, close the shutoff valve at the pressure gauge. Depress the lever slowly and listen for any chatter noise. The nozzle may make a hissing or squealing noise rather than a distinct chatter. This is acceptable. These sounds tell you the internal parts are moving freely and are not defective. If the nozzle will not chatter, even when the lever is pumped rapidly, it should be considered defective and not usable. In fact, if the nozzle fails to pass any one of the tests we've just seen, it should be replaced. On the other hand, Bosch 6.2 nozzles that do pass these tests are likely to have a satisfactory spray pattern. As mentioned earlier, spray pattern testing is not a meaningful test for Bosch 6.2 engine nozzles. Spray patterns for other types of nozzles should be checked for proper fuel atomization only. The spray should be well atomized with no droplets or stream-like flow within 1/2 inch of the tip. Any malfunctioning nozzles should be further checked and possibly repaired at an authorized repair location. This Truck Service Bulletin 83B55 gives you the latest nozzle testing procedure for the 6.2-liter Bosch nozzles. Procedures for other nozzles can be found in the appropriate service repair manual. Output is important, since an uneven output between cylinders can cause rough idle. The greater the difference in output, the more likely that idle quality will be unacceptable. The glow plug resistance procedure lets you determine the relative output of each cylinder. Checking glow plug resistance also gives you a means of tailoring nozzles and lines to a particular engine pump combination, which will help smooth out idle quality. The resistance at each glow plug is directly proportional to the temperature in each cylinder, which means that it's also proportional to the output at each cylinder. Use the Kent Moore high impedance digital multimeter, tool J29125, to measure resistance. When using it, select your scales in the following manner. Set the left-hand switch to ohms. Turn the right-hand switch full counterclockwise 200 ohms and slide the center switch to the left, DC low. Next, start the engine. Turn on the heater and allow the engine to warm up. Remove all feed wires from the glow plugs. Disconnect the generator 2-lead connector. Then, using MagTac J26925, adjust engine speed by turning the idle speed screw on the side of the injection pump to the worst engine idle roughness, but do not exceed 900 RPM. Let the engine run for at least 1 minute until the thermostat is open and the upper radiator hose is hot. Next, attach an alligator clip to the black test lead of the multimeter. And remember, the clip must be grounded to the engine and remain grounded to this point until you've completed all the tests. After grounding the clip and observing this caution, write down the engine firing order. With the engine still idling, probe each glow plug terminal and record the resistance values for each cylinder in firing order sequence. You'll find that most readings will be between 1.8 and 3.4 ohms. If they're not, turn off the engine for several minutes and then repeat the glow plug resistance test. They should now read 0.7 or 0.8 ohms. If this reading is not obtained, check the meter for correct settings. Check for a low or incorrect battery. And check the meter ground wire to the engine. When checking resistance, remember, a high resistance reading indicates high power output, and a low resistance reading indicates low power output. This is so because, as previously stated, resistance values are proportional to cylinder temperature and therefore proportional to cylinder output. The higher the temperature, the greater the resistance. Now, assume you have a low resistance reading, which indicates low power output. Let's say that the reading on any cylinder is about 1.2 or 1.3 ohms, which would be low. This would indicate a possible problem with the injection nozzle or high pressure line to that cylinder, or an engine mechanical problem. Check the compression of the low reading cylinder and the cylinders which fire before and after the low cylinder. Correct any cause of low compression before proceeding to the fuel system. The results of all cylinder glow plug resistance readings should be carefully checked with an eye to spotting any wide variations. Usually, rough engines will have a difference of 0.3 ohms or more between cylinders in firing order. Although not a part of the fuel system, cylinder head leakage problems can show up as low power and rough running complaints. New procedures have been developed to deal with this problem. External engine coolant loss on the 6.2 diesel has generally been from rear lower corner on the left-hand cylinder head and the front lower corner of the right-hand cylinder head. This coolant loss condition is the result of inadequate sealing around the core cleanout hole in the cylinder head. A contour-shaped brass plug, part number 14079-353, has been developed to seal this hole. Whenever a cylinder head is removed for service, check this area. If there's no plug, or if a plug has previously been installed and its appearance is questionable, a new plug should be installed. Here's the procedure. First, use a file to remove any casting irregularities, burrs, or roughness from the core hole and break any sharp edges. Coat the sides of the hole and the plug with Loctite, number 620 or 271, or use GM kit number 1052-624. Using a press or vise, slowly push the brass plug into the hole, using a flat steel plate to squarely load the plug. Press in until the plug is flush with the head surface. Do not use a hammer directly on the plug, as this might damage it. Allow the Loctite to set about 30 minutes before installing the head. To reduce head gasket coolant leakage conditions, a new head bolt torquing procedure has been developed which should be used whenever a new head gasket is installed. The new procedure is based on methods long used on heavy-duty diesel engines and in the aircraft industry. It's called the torque and angle turn method. It provides more uniform clamp load to help prevent cylinder head leakage. The procedure should be used on all 6.2 engines to correct external and internal leak conditions. In performing the torque angle turn procedure, be sure to remove all the old sealer from head bolts and head bolt holes with a wire brush. Also, check the head and block for warpage. Each surface should be flat within 6/1000ths of an inch overall, and in any 6-inch area, it must be flat within 3/1000ths of an inch. If the head does not meet these specifications, it must be replaced. With all surfaces wiped clean, install a new gasket over the dowel pins. The pre-chamber shields on the gasket must face up. Use this green Victor gasket, part number 14066-260, if the problem was an internal coolant leak, or this red Felpro gasket, part number 14066-246, if the problem was an external coolant leak. When replacing the head, use a sealing compound on the bolt threads. The compound should be part number 1052080 or equivalent. Also, all bolts are to be tightened as shown here, starting in the center and working toward the ends of the head. As the first step, torque each bolt in sequence to 20 foot-pounds, or 25 Newton meters. This will seat the bolt. Second, torque each bolt again in the same sequence to 50 foot-pounds, 65 Newton meters. Then, as the next step, rotate each bolt 1/4 turn, that is 90 degrees, again in the same sequence. The final step is to check each bolt for a minimum of 100 foot-pounds of torque. Do this in the same sequence as used for torquing the bolts. If any bolt is under 100 foot-pounds, tighten it to that specification. Summarizing the procedure, torque the bolts to 20 foot-pounds to seat them. Retorque to 50 foot-pounds, and then rotate each bolt 1/4 turn, all in the same specific sequence, each time. Finally, check for a minimum torque reading at each bolt of at least 100 foot-pounds. Tighten to the specification if necessary. This is a new head bolt for the 6.2-liter engine. The longer thread length increases the bolt's stretchability, which in turn increases the bolt's ability to retain clamp load. You should use these new longer thread bolts whenever you remove and replace a cylinder head on a 6.2 engine. These new bolts, together with the torque and angle turn procedure we just reviewed, will provide a more uniform clamp load that greatly reduces the possibility of leakage.